I want to look at an application of the temperature composition curve that might be of particular interest to you if you work in a chemistry lab. And that has to do with fractional distillation. It's a common technique we use to separate the components of a mixture. And it turns out that if we have volatile components in a solution that have different boiling points or different vapor pressures, then this is can be a very effective way for separating them. Now I'll remind you that we're still maintaining our convention that the second component has the higher vapor pressure than the first component, so it is the more volatile of the two, which also means that its boiling point is going to be below that of the other one. Now I've tried to save a little time by pre-drawing a temperature composition curve here, but I have limited to how much I've labeled on it. So for example, this red curve up here at the top is the vapor curve. So we have vapor up here in the top part of the diagram, and in the bottom part of the diagram we have the solution. So this blue curve is the solution curve. And in between these two curves is really a region that will represent a liquid-vapor equilibrium, or a coexistence region. So it is, remember, these are all cross sections of a phase diagram involving the binary mixture, and so this is just a particular cross section of that. Now I haven't labeled the bottom, but of course it is, as usual, the mole fraction of component 2. And I'm not going to specify whether it's solution phase or vapor phase because we're going to plot both of these as time goes by. All right, but this is the mole fraction varying from 0 to 1, so the boiling point for 2 is over here on the right hand side, and it is lower than the boiling point for component 1, which is up here on the upper left hand side. Now I want you to imagine that we're starting with a mixture that, for example, might have this mole fraction for the component 2. Now as we take this mixture and we heat it up, we would eventually get to this curve here, and at this point, which I can call the boiling point for this particular solution, so I'll call that T-boil, our solution is going to begin to boil. All right, but once it begins to boil, remember, the more volatile of the two components is going to be enriched in the vapor phase. So in fact what we'll find is we have to draw a line across here. This indicates the mole fraction of component 2 in the vapor phase from having done this. So let me draw this on down. So this would be Y2 in this case. All right, and if that's the end of the story, then okay, great. We've basically boiled a little bit of 2 off of the solution, but in fact the vapor still has a substantial fraction of component 1, and the liquid still has a substantial component of component 2. So this doesn't really help us separate these two components from one another. However, what if we decided to capture the condensate of this particular species? In other words, this mixture, which is different from the original mixture. So I want to write over here on the right hand side, I want to write down that our original mixture had composition X2, so this is original, and that's in the solution phase. When we boiled it and put stuff in the vapor, that was less than Y2, which is the mole fraction of the same component in the vapor phase. But now what I want to do is I want to condense this back down into the liquid phase, so down in here somewhere, and then reboil it so that it's going to boil here. All right, so what that will do is now create a vapor that has this composition. And look what we've done in 2 steps. So this is Y2 prime. In 2 steps I've gone from a mole fraction way over here to a mole fraction over here, but this is in the vapor phase. Okay, so this mole fraction in the vapor phase is now substantially enriched. So in effect what I have done in the middle here is I have created a second starting component, X2, and then boiled it again to create a second component Y2. So I probably should have labeled this as 2. All right, so as we move along, we are successively enriching the mole fraction of Y2 as we go. And this is the basic strategy behind fractional distillation. It's basically a series of steps where we'll capture the vapor phase from each step, reboil it, get a new vapor phase mole fraction, and each step along the way will enrich it farther and farther until we have essentially pure component 2 in the vapor phase. And if we play our cards right, we have pure component 1 in the liquid phase. But how can we do this? Well, I've drawn over here on the right not so elegant drawing of a fractional distillation apparatus that you might have in the lab. So you've got your Bunsen burner here heating up our liquid. This is our mixture that's being heated up in this flask. And now this column that it's going up to into is a packed column. And by packed, I mean it's got a bunch of little spheres, glass spheres, that provide a lot of surface area. So what's happening with this liquid as it goes up in here is that, first of all, it had to evaporate from the solution phase down here, and it then travels as a vapor up to this column. But those glass beads in the column are not at the same temperature as this very hot flask down here. So what happens is that those that the mixture in the vapor phase will now begin to condense on those beads. But as more hot gas comes up through the column, it will reboil that mixture. And since the volatile part of the mixture is the one that is preferentially being enriched as we move up through here, and it has the lower vapor, has a lower boiling point, we'll be able to reboil that mixture several times as it's traveling up through this column. So in effect, what we're doing in the column is a series of steps, just like I've drawn here in the temperature composition diagram. So in effect, this is what's happening in the column. And at the end of the process, we'll end up with something that actually is down here and represents fairly pure component 2. That's what will ultimately escape through the top here through a condenser. I didn't draw a condenser, but you can imagine a condenser up here that causes this to escape through the top and be collected then as a separate flask, in a separate flask. All right, meanwhile, what's left behind here will increasingly be an increasingly rich solution in component 1, and if all is really working well, we might actually get a full separation of the two. Now, I'll say in practice that we typically are going to have better luck separating the more volatile of the two components using a fractional distillation method. But this process that I've outlined is actually very similar to a process that's used industrially for fractional distillation. And in fact, you've probably seen some of these driving by in your car. This is exactly what we do with petroleum to separate it into various components that we can use for different things. So one component might be used for fueling your car. Another component might be the butane that you put into a cigarette lighter. Another component might be something heavier that you might use for asphalt tar or something like that. But in any case, industrial distilleries would use a fractional column like this to separate the different components that you find in a petroleum mixture from one another so that we can use those pure components for something useful.